As we start to look at chemical reactions, it's important for us to keep in mind the things that encourage reactions to proceed. One is the formation of a solid, the formation of water, the transfer of electrons, and the formation of a gas. When we're working with aqueous reactions, those are reactions where the substances are dissolved in water, one of these four things will help encourage the reaction that will generally happen. What we want to look at now is the balancing of chemical reactions. So let's take a look at this first from just a pictorial representation. Here we have a chemical equation that represents the formation of water from hydrogen and oxygen. Notice that the hydrogen and the oxygen are diatomic, so they're listed as H2 and O2. The G represents that they're in the gaseous state. They're going to be converted into water, and water, we know that the formula for that is H2O, and we'll have that in the liquid state. And above we have two different supplies of these. So if I go up to the top and I bring down a molecule of hydrogen that I can use, and I'll bring down a molecule of oxygen, right? And to make water, I'm going to need one of those oxygen one of those oxygen atoms, and I'm going to need both of the atoms of hydrogen. Although, there we go. So there we go. There's our one water molecule we've made. But you see that we have a lone oxygen here that hasn't reacted with anything. So we're going to need another molecule of hydrogen. Bring that down. And let's bring that over as well. Bring our oxygen over. And we've now made two water molecules. So if I go back and do a little recap here, I know that I used two molecules of the element hydrogen, one molecule of the element oxygen, and I ended up forming two molecules of water. And so this would represent the balanced equation for the formation of water from hydrogen and oxygen. The first method for balancing equations we're going to use is called the guess and check method. Although it does involve guessing, there's some things that we can do to make this a little more organized so that we're not just randomly putting in values to balance the equation. First of all, the numbers that we're putting in front of the substances are called the coefficients. Remember that we can't change the subscripts, as that would change the identity of the substance in our equation. So the first thing we want to do is put a 1 as the coefficient in front of the most complicated substance. Most of the time this is going to make the equation a little bit easier to balance if we start there, and it's a good place to start. Number 2 is that we're only going to work on one element at a time. So we're going to take a look at the elements that are in the substance where we put the first coefficient. We're going to pick one of them to work with. Tip number 3 is to always work from a known coefficient on one side of the equation to an unknown coefficient on the other side of the equation. This is called the Tarzan rule. And then finally, tip number 4, save hydrogen and oxygen for last. These two elements tend to occur in several places in equations, oftentimes. And so if you save those for last, it'll save yourself a little bit of a headache. And tip number 5 we'll come back to in just a moment after we do a practice on this with tip numbers 1 through 4. So here's an equation for the combustion of methane. So once I have the substances listed correctly with the correct subscripts and the correct states of matter, now I'm going to balance. So in this one, you would look at this and, perhaps the methane would be our most complicated part there. So let me just put in an image here for us to take a look at, just to think about. Although we don't have to draw these pictures every single time we do balancing, but it helps to kind of keep in mind what we're doing here. So you can see that obviously it's not balanced the way that it is. You've got yeah, 2 of the yellow oxygens on the left, but you've got 3 on the right. There's 4 hydrogens on the left with the methane, but only 2 of the hydrogens in water on the right. So balancing this, we're going to use our rules. So we're going to put a 1 in front of the methane, and I'm not going to start with hydrogen. I'll start with carbon. So I'm going to swing over from the methane, Tarzan rule, to the CO2, and I'm going to put a 1 in there so that I'll have 1 carbon. Now, everything that's left are oxygen and hydrogen, so we have no choice but to go to those. So I'm going to go back to my methane, and there's 4 hydrogens in the methane on the left. And then I'm going to swing over to the water on the right. Now, it's important, just a way to think about this, is to, until you put a coefficient there, you have no atoms of that element. So if we have 4 hydrogens on the left, we swing over, until we put a coefficient there, we have no hydrogens. But what I want to do is end up with 4 hydrogens, so I can put a 2 in front of the water as a coefficient, and then that would give me 4 hydrogens. And now the only thing left is the oxygen, so I go over on the right-hand side, and in the carbon dioxide I have 2 atoms of hydrogen, 1 of the molecule, each molecule has 2, and the water, there's 2 more oxygens there. And so I'm going to swing over here, and again, I don't have any oxygens at first, but in order to get 4, I'm going to put a 2 as the coefficient in front of oxygen. And so this should represent our balanced equation. And so here we have the pictures for this, and sure enough, now we have the same number of atoms of each element on both sides. So you can see it's a systematic approach, but it'll help make equations a little bit easier for us to balance. All right, now rule number 5 is what I call the odd-even rule. The odd-even rule applies when you're going through the other rules and you realize that you have an odd or an even number on one side, but you need the opposite. So for instance, you have an even number or you have an even number on the left, but you need an odd number on the right, or vice versa. So if we use water as an example here, without the pictures, if we were to balance this, we put a 1 in front of the water, most complicated part. That gives me 2 hydrogens, and so I can swing over to the other side and put a 1 in front of the H2, which gives me 2 hydrogens there. So the hydrogens are good. But now I look at my water molecule here, and there's 1 oxygen there. When I go to swing over to the left, I can't get 1 oxygen. I can only put in a whole number for a coefficient. So this is that odd-even rule that I was just mentioning about. It's important not to panic here. What we want to do is stop, take a deep breath, don't panic, and then what we're going to do is we're going to double each coefficient that we already have in place and then try to balance again. All right, so double each coefficient we have in place. So I'm going to make that one a 2. I'm going to make that one a 2. By doubling each one, we guarantee that we keep the elements balanced that we'd already put in there. So now we have 2 oxygens on the right, and in order to get 2 on the left, all we do is have to put a 1 in front of the O2, and we now have a balanced equation. Notice that I don't erase the 1s. I just cross them out and put a 2 above it, and then that'll be fine for what we're doing right now. If we use this systematically, we can even do equations that are much more complicated, such as the one here. Again, just following a kind of systematic approach. The most complicated part up here would probably be the substance at the beginning, so I would start with a 1 there. Now notice that here we have an equation that has brackets in it. So if I were to just kind of isolate that part for just a moment and see what that means. So the 2 represents 2 of everything inside. So I've got to remember that this part of the formula tells me that there are 2 phosphorus and 8 oxygen. So I just have to be careful of that as I'm going through the balancing. So let's start with the sodium. We have 2 sodium there on the left with that 1 there. So in order to get 2 sodium on the right, I'm going to put a 2 in front of the sodium nitrate. Then I can approach and do the tin. So there's 1 tin over on the left. I'm going to swing over and put a 1 in front of the tin for nitrate to get 1 tin over there. So moving along okay. Next I have in this one, again looking at the phosphate part of this, there are 2 phosphates on the left because you have 1 of the whole thing and each one has 2 phosphates. So now I swing over to the right and I see that right away I've got a problem here because I need to have at least 4 phosphorus on the right. If you look at the tetra phosphorus dioxide. So I'm going to go back over and I know I have to have at least 4, so I'm going to double everything that I've written already. And again, this guarantees that all the things that I wrote up there before will stay balanced. Okay. Now I find that I have 4 phosphorus on the left, and so I can put a 1 over here to get 4 phosphorus. Again, leaving the oxygen for last, I can do nitrogen. So if I look over on the right now, I see that in the sodium nitrate I would have 4 nitrogens. In the tin, I have a SN, there's 4 of the nitrates in one of those, and there's 2 of those total formulas in the equation. So that would give me 8 nitrogens there. So we have 8 nitrogens here, 4 nitrogens here. So it's a total of 12 nitrogens. So I'm going to put a 12 in front of the HNO3. All right, now we've left ourselves with just the hydrogen and the oxygen. There's oxygen in literally every single one of these. So that might not be the best one to actually look at right now for balancing the water that's left. So let's just look at the hydrogen. Over on the left, with the HNO3, the nitric acid, we have 12 hydrogens. To get 12 hydrogens on the right, we would need to put a 6 in front of the H2O. All right, so here we balanced everything. It might be helpful if we draw kind of a line there where the arrow is for the reaction so we know where we're working from. But we filled in all of the coefficients. We haven't yet checked on the oxygen. The oxygen should come out well, and if you have time after you balance this, it would be a good idea to go through and just double check and make sure the oxygens are balanced. But as you can see, an equation that's fairly complicated can be balanced fairly efficiently if you just follow the 5 tips that I've provided for you. All right, so good luck balancing the equations, and mostly it's just a matter of practicing and you'll get rather fluent with balancing equations.